Even when our ultimate goal is to compare the effect of two different treatments, there's still a target population in mind. So if we think about this question of comparing the effect of knocking on someone's door versus not knocking on someone's door on whether they vote in a particular election, we still would have started out by defining the target population of all doors, all households we care about, and then defining a sample population that may or may not be a subset of that target population, and then think about how to choose a sample of households or doors from that sample population. And this picture is the one we've looked at before. And the idea is we have to think not only about how this sample was selected from the sample population, how we chose which doors to include in our study, but also within that sample, we have to think about how we're going to decide who gets which treatment. So there are two steps here, two reasons for the uncertainty, two different reasons that we can't just calculate the S-demand. The first reason is that we sample from the sample population to get a subset of the units in the target population. And the other reason is that once we have that sample, we divide it in terms of who gets which treatment. So we're still not going to have all the information we need in order to just calculate the effect of treatment. So let's focus on this second step now. We're focusing on this idea that within a sample that you've selected from a sample population, you need to assign or notice that some units have been assigned to one level of treatment versus another. So here we're thinking of treatment as whether a particular potential voter has their door knocked on before the election. So the unit's going to be the potential voter here. Now, I'm going to replace these smiley faces with symbols that show the underlying characteristics of these voters. Each of these voters is either male or female. Now, male versus female is not the treatment. What I'm interested in is the effect of having your door knocked on versus not, but each of these units have underlying background characteristics. And in this little graphic I have here, half of the voters in the sample are male and half are female. And the idea is that I'm going to select some of the units in the sample to have their doors knocked on, and others are not going to have their doors knocked on. Suppose that the 6 units in this black rectangle are the ones whose doors I knock on. Think for a moment about the problem with that. If I knock on the doors of the people in this black rectangle, and I do not knock on the doors of the people who are outside of the black rectangle, then I won't be able to tell whether any differences between the people who have their doors knocked on and the people who don't have their doors knocked on are due to the knocking or due to the gender. In other words, all the people of one gender have their doors knocked on, all the people of the other gender don't have their doors knocked on. This is an example of a way to assign treatment, a way to assign who gets their door knocked on that's not particularly useful for learning about the treatment effect. Here's a different way I could do this. I could have everyone in this black rectangle have their door knocked on and everyone outside this black rectangle not have their door knocked on. Still, the proportion of men versus women is different among those who have their doors knocked on than among those who do not have their doors knocked on. So still, this is not an ideal setup for learning about the effect of knocking on the door on voting, because if more of the people in the black rectangle end up voting than the people outside the rectangle, I don't know whether that is due to the knocking versus not knocking or due to differences in the baseline gender characteristics. So this would be the ideal setup, that the people whose doors I knocked on would have the same gender makeup as the set of people whose doors I don't knock on. What I want you to see here is that this process of deciding who ends up in which treatment group within a sample is parallel to deciding who, from a sample population, we should even include in our sample. In both cases, we're focusing on getting a representative group. When we sample from a sample population, our goal is to get a representative sample. When we decide who within a sample is assigned to which treatment group, our goal is that the two treatment groups will be representative of each other. So I'm going to mention 2 ways to select treatment groups within a sample. One is called complete randomization, and that's parallel to a simple random sample. Complete randomization means that you put all the names of the units in your sample into a hat, and you randomly draw some of them. That's complete randomization. It's parallel to simple random sampling, which meant that you put all the units in your sample population in a hat and draw some of them to create your sample. And then there's also stratified randomization, which is parallel to stratified sampling. And this would be akin to putting all the names of the women in my sample in a hat and randomly drawing some of them to have their doors knocked on, and also putting all the names of the men in my sample in a hat and randomly drawing some of them to have their doors knocked on. And that's going to guarantee that among the people who have their doors knocked on, there will be both men and women, and among the people who do not have their doors knocked on, there will be both men and women. Randomization is the best way to assign treatment groups if you're interested in learning about causation. It's not the only way, but it's the best way. So again, we started with this idea that if we had all the information we would need in order to calculate our estimand, we could just stop and calculate our estimand. But rarely is that the case, and there are two reasons we've mentioned. The first reason is that we typically do not have information on every unit in the target population. Rather, we have information on a sample of units, and we hope that sample is representative of the target population. That's one reason we cannot just calculate the estimand. The other reason we cannot just calculate the estimand if we're interested in learning about the causal effect of a treatment is that even within that sample, some of the units are assigned to one treatment, some of the units are assigned to the other treatment, and we don't know what would have happened to each unit had she been assigned or he been assigned the other treatment. There's two reasons for uncertainty, and what we're hoping is that each treatment group within the sample is representative of the entire original target population.